warm welcome to all my friends. A very good morning, good afternoon, good evening. This is the Total Quality Management 1 class and I am Raghunandan Sengupta from the IME department, IIT Kanpur. And we are starting the 29th lecture, which would be the second last in the 6th week. Now we were discussing the charts, and if you remember, to recap for the last 3-4 lectures, we did discuss about the X bar charts, the central line for the X bar charts being the X double bar, which is the expected value of the distribution from where you are taking. Then we had the concept of the R charts, which was something to do with the range. Then we had something to do with the standard deviation of the sample, where information is known about the standard deviation of the population and not known. So, you consider that. Then we consider that depending on the coefficients. Now, coefficients would be what level of efficiency you want, or what is the level of confidence which you want. You would basically have those coefficients as in all the examples we considered as 3 plus minus 3, because you wanted to cover about 99% of the overall coverage area, which is plus minus 3, and that is the total is 6 sigma. Then we considered the NP charts, P charts. P was the proportions, NP was the again something to do with the proportions, but when multiplied by the sample size gives you the total numbers in the sample, like it is something to do with X being the total number, the indirect way of calculating. Then in all the cases we considered the so called central limit theorem to be true, and we considered the distribution to be normal, and we took the mean and the standard deviation for the actual population based on which we are trying to infer from the central limit theorem, and we completed. So, continuing our discussion, so variable sample size. So, we are going to consider the variable sample size. Till now we have considered sample size to be fixed like n, and number of samples we took was m as in mango or mongoose. So, depending on that we found out what was the average or the double average X bar or R bar, whatever it was. So, in the variable sample size, in the first method is variable with control limits. So, you would have some control limits for the variability, and the variability is there for the sample size. The most simple approach is to determine control limits for each individual sample that are based on specific sample size. So, n is the sample size, we will keep taking n observations, set of observation each time, and do our studies accordingly. In case if it is not, like where the number of such sample space, if the product which you are producing is very less in number, like you are producing some very unique component for a spacecraft which your company is manufacturing, or you are producing some electronic gadget for the fighter aircrafts, or say for example for some tanks which will be only produced only once. So, obviously, the number of samples which you will get for those products which will be used in as a component in those machines, which will be a part of either the tank or the spacecraft or the fighter planes, are limited. So, now obviously, you will take the study or take the samples in such a way that the variability of sample size would definitely come. Or say for example, you have a production process where products are being produced, that is true, but you have to do some destructive sampling, and that becomes very costly for you. So, obviously, you would like to reduce the sample size, because the observation which you take need to be destroyed in order to basically study them. So, in that case sample size would also vary. So, the most simple approach, as I said, is to determine the control limits for each individual sample that are based on specified sample size. Now, if the ith sample is of size ni, so n suffix I is basically for the sample which you are taking at what time, depending on that stage your sample size will change. Like say for example, 9 o'clock in the morning you take the first sample and the sample size is 20. Then again 10 o'clock in the same day morning you take a sample size which is now n2, but say for example the sample size is 19. Again at 11 o'clock in the morning you take a third sample which is of size n3, which is the third sample you are taking, and the size is say for example 10. So, obviously that will change the sample size based on which you will try to recalculate. So, let me highlight the formula first. So, this p hat bar which you have is the best estimate for the proportions. Proportion means how many some number of defects and so on and so forth they are there. This parameter 3 which is coming for plus minus 3 sigma. Now, for the proportions for the binomial distribution, we knew this would be the standard error or the best estimate for the population standard deviation. Now, in case p is not known, you will replace p with p hat, q with q hat, and this p hat is basically p bar, and this q hat is basically 1 minus p bar. Then, if you have the average value central line given by, I will change the color, is this one. This will be for this one with a minus sign. Now, if the ith sample size, as I was saying, that is ni, formula remains the same. Only thing which changes is this ni. So, technically it should be n, because sample size from reading to reading is same, but if they are changing, obviously you will have n1 for the first case, n2 for the second case, and so on and so forth. Now, let us study in details with an example again for Montgomery. The first column are the sample numbers, which is I 1, 2, 3, 4 till 25th one. So, you are taking 25 such samples. Now, it was a fixed sample size, then the sample size would be fixed, say for example at 20. So, the total number of observations would be 25 into 20. Now, see what you are doing here in this case. The sample size are changing. So, in the first case, let me highlight again, it is 100 in number, while in the last case 25th one it is 19 number. So, the total such additions would be basically the sample size comes out to be 2450. The number of non-conforming defects are given by D1, proportions are given by 12 by 100, which comes out to be 0.12. Similarly, for the last one 0.1, it becomes 9 by 90. From there you have the total set of proportions defect, which is the so called would be the average values, you can find it out. So, total 2.383 would be the proportions, which is di by ni, and obviously you have to find the average of that. Now, from this standard deviations you find out the values, which is sigma hat is basically the variance or the standard error. So, standard error square or variance. So, you want to find out the standard error or standard deviation, you need to find out square root of the variance. Now, if you are thinking from where this value is coming, so this would basically be calculated from here. So, you have 2.8383 as the p hat sum of the p hats for all i's, I going from 1 to 25, you add them up and divide by 25, which is the number of readings. Then q would basically be given by 1 minus p hat, and then you obviously you go into the formula. So, I should remove the highlighter, go to the sketch, use the sketch pen. So, basically it will be p plus p hat or p bar, plus would be for the upper control and minus would be for the lower control. This 3 value would come because you want that level of confidence, and this would be p bar into 1 minus p bar by n, and you will do the calculations accordingly. Ni's, sorry, so Ni's. Now, here is the calculation. For the 25 sample size, we calculated the total sum of number of defects is 234, total number of observations which you have taken is 2450. Hence, this value comes out to be 0.096. The value of Q bar would be 1 minus this, you can find out. So, here you can find out the central line comes out to be 0.096. The upper control will be 3 plus sigma, that comes out to be the value as given here, you can calculate it. The lower control limit would be the P bar minus 3 sigma hat, which is the estimated value, and this sigma hat you know, again I am repeating, and you can find it out accordingly. Now you want to find out the control limit based on average sample size. So, sample size is changing and you want to basically use the average sample size. This assumes that future sample size will not differ greatly from those previously observed. So, there would be difference, but the difference is not large. So, what you need to do is that if you check here, you had taken 2450 total number of observations. How many such times you have taken the observations was 25 in number, because in one time you took 100, another time you took 90, sometime you took something else. So, there are 25 such. So, on an average you may have taken at each go 98 observations. Based on that you again, but now in that case ni's don't come, actually n would come, where n is n bar, which is what you have calculated, which is 98. Based on that you find out P bar or P hat comes out to be 0.096, and the upper control and the lower control values are 0.185 and 0.007. Control chart for non-conformities or C charts. So, now initially if you remember, we have considered the x bar as for the average. For the dispersion we first took the range and then basically replaced it with either the standard error or the standard deviation. Then we took the concept of n into P charts and all these things. Now we will try to use the concept of non-conformities, which is also in some way the concept of proportions. So, each specific point at which a specification is not satisfied results in a defect or non-conformity. So, obviously it would be good or bad or black and white, whatever the outcomes are, there would be two outcomes, and one is as per your satisfaction, other is basically not non-conforming, which would be otherwise. A non-conforming item will contain at least one non-conformity. So, say for example, you are checking 3 types of defects. So, consider them to be length, some product is being manufactured, you want to find out the length, the breadth, and say for example, the color, quality, or whatever the item is. So, if one of them is not according to the standard, obviously you will not consider them to be conforming to your specification. So, it would be a non-conforming product. Depending on the nature and severity, it is quite possible for a unit to contain several non-conformities. So, it may be possible that the first object which you took, the example which I gave few seconds back, length, breadth and color type, what like you consider this, you are producing some types of high quality tables or chairs, and the table has very specific specifications which will be used, say for example, in a high star 7-star hotel, and obviously the hotel owners want the specific coloration to be exactly matching to one color shade, and you as a company are producing those tables which have to basically fitted in either in their high class restaurant of this hotel chain or wherever it is, and you basically check the length, breadth, because the dimensions has to be specified as given by the hotel owners or the company which is ordering those tables, and the color conformity also has to be there. So, it can be either the table, if it is confirmed as per the standards, so obviously length, breadth and color would match. In case it is not, it can be that one of the non-conformity is there, which may be either the length or the breadth or the color, or it can be more than one also. So, this is what is mentioned. A non-conforming item will contain at least one non-conformity. Depending on the nature and severity, it is quite possible for a unit to contain several non-conformities and not be classified as non-conforming ones. So, consider these. Suppose we are manufacturing personal computers. Each unit could have one or more very minor flaws in the cabinet which you try to basically finish and make it, and since these flaws do not seriously affect the unit's functioning, it could be classified as conforming. So, the example which is being given is that there would be many different type of non-conformity. So, now you have to basically decide on the severity of the problem, that what are the set of non-conforming errors and what are the set of conforming errors. Errors means that even if, say for example, the error is within a particular non-conformity norms, still you will basically consider it to be applicable and you can pass it. Consider this example. You are measuring, say for example, a very simple lawn mower, and the lawn mower would definitely have some amount of error either in the shape and size of the grass cutter or the shape and size of the handle. So, any plus minus centimeters or millimeters in change in those specifications are allowed, and you definitely you will consider them, that even if they are not exactly meeting the standards, you will consider them to be under the purview of conformity and will pass it. But if such problems or such issues comes out for a very high standard product, consider like this, a very high valued product or component which will be used in the airline industry for the aeroplane to function, or say for example, the type of pacemaker which you will supply to the heart patient. So, in those cases, not a single error would be there, and obviously the non-conformity in the long run should definitely be 0. So, continuing in this, if there are too many of these flaws, the personal computer should be classified as non-conforming, since the flaws would be very noticeable to the customer and might affect the sale of the unit. So, maybe the number of non-conformities are very less and those can be passed, but if the number of non-conformities or the type of non-conformities are very large or they are very serious, obviously that is a problem, and you have to basically take corrective actions later on to rectify that, and obviously those considerations should be studied when you are doing the non-conformity or the conformity calculations and trying to draw the charts. So, as I did mention for that there may be many errors, less errors for the computers. The standard control charts which we will consider is that such a control charts, if whatever the information is, we will first try to convert into a standard normal table and use the standard normal distribution. Now, coming back to the standard normal distribution and the concept which is there, generally we know this is true, where x is a distribution which is normal with certain mean which is sigma, this mu, and variance is sigma square. Now, when you want to convert into a standard normal, obviously you use this transformation which I have just put in a box. Now, for the case of this binomial distribution, where that is either good or bad, black and white, yes or no, whatever, what you want to actually understand is that your actual mu value is basically the proportion which is p. Now, in case you want to basically utilize the value of mu from the sample, obviously the sample estimate would come up which is x bar n, considering the normal distribution, that is the best estimate, UMVUE, which is uniform minimum variance unbiased estimator. Now, for that case, obviously the variance would be, say for example, in the normal case would be sigma square by n, which is n is the sample size. So, if we use this concept, obviously it will become, now the best estimate for p would basically be p hat. So, which is a 1-to-1 correspondence to x bar. Now, that what we have, it is basically that estimate, and we find out the difference between the estimate and the parameter. So, this p value is basically mu here. Now, in the denominator, if you see, we divide it, say for example, with the value of n, which is the sample size. Now, if I consider the idea of trying to find out, say for example, the sample variance, which is the best estimate for the population one, obviously you had sigma square by n. Now, in this case sigma square by n would be, this whole terms would be replaced. Obviously, you have to find out the square root of that, would be sigma by square root n. So, this becomes technically p, obviously in that case p hat would be there, p hat into 1 minus p hat, which is q divided by n whole square. This is the formula for the binomial case. So, this comes as a replication of dividing it by sigma, which is you are trying to basically transform and normalize it. So, once you normalize it, you have the formula which I am trying to basically put as a green color. So, this would be the standard normal deviate. Now, what you will do is that you will try to use the standard normal deviate tables and utilize this. So, based on that you will draw the diagram, find out the values and basically conclude accordingly. So, in that case the central line which you will try to draw would be the p hat, or the actual value, if it is possible for you to know, would be p. The corresponding deviations plus and minus whatever coefficients multiplied by sigma would be, sigma value is that what you have in the denominator, which is square root of p into 1 minus p by n. So, if you would want to basically have 6 sigma limits, obviously it will be plus minus 3. If you want to have 4 sigma limits, again it will have basically plus minus 2. So, continuing the discussion, here p means the process fraction non-conforming as in the and in the in control state. So, based on that you will try to find out that what are the values of the mean and the values of the standard deviation, based on which you will do the calculation, and before that you will convert that into a standard normal distribution of the values. So, for the problem which we just discussed, so the sample fractions non-conforming are given by p hat, which is the best estimate for p, as I told, and the sample numbers are given along the x axis 1, 2, 3, 4, so on and so forth till the 25th one. And when you basically chart it, the values are given as the diagram here. So, I will try to utilize the green one. So, where I am highlighting, this is basically the chart which gives you the control charts for the fraction non-conforming with variable sample size. And when you try to draw the control charts for fraction non-conforming based on the average sample size, if you remember, the average sample size was 2450 divided by 25, while in the variable sample size and the average sample size came out to be 98. Now, if I am trying to utilize the variable sample size, the diagram is shown, which in figure to 7.6, which I am just circled in green color. And if I use the concept of, say for example, fixed sample size, which is in method 2, where the sample size was basically 98, the upper control limit, the lower control limit and central lines are drawn, and based on that I get the table which is given in figure 7.8. And here for all these cases, the actual sample size, remember, that would be fixed, it is not varying much, but in the initial diagram which is given in figure 7.6, they are varying because the sample size in each reading is varying. So, obviously from there you can draw meaningful conclusions based on which how they are performing. Now, remember one thing, which I think everybody would have understood, but I will still highlight it, and I will try to highlight it using, say for example, the violet color. So, if you see many of where the stylus is now focusing, this one, this small lines which are drawn, these are the changing limits which you have for the upper control limit and the lower control limit, because if you remember, ni's are changing. If ni's are changing, the p hat, which is the p double bar or the p single bar, whatever the proportions you have, that central line is fixed. But the upper control limit and the lower control limit, whatever change which you have is plus minus the square root of p into 1 minus p divided by n. So, that n is changing from reading to reading, from sample 1, sample 2, sample 3, sample 4, it is changing. As it is changing, the upper control limit values are also changing. So, that is coming out here. So, I will try to basically remove the highlight in order to basically make it clear. So, this is what is. So, if you consider where I am basically now erasing, you see small horizontal blue lines. So, these are the upper control values for each and every single change of the sample size. And similarly, when I go to the lower control limit, again these values are shown by small vertical line, these horizontal lines, which basically signifies the lower control limit for different sample sizes. In method 3, which we use, as we discussed, if we use the standard control charts for fraction non-conforming, and based on that if we draw it, fraction non-conforming would also be somewhat similar to the P charts. Here the upper control limit and the lower control limit would be plus and minus 3. Why they are plus and minus 3? Let me make it very. Now, you have already converted Z using the x into Z using the standard normal deviate. Now, the interesting issue is Z has a distribution normal with 0 mean and 1 standard deviation and 1 error. So, if you with this information go back to this table which is shown, which is figure, or that figure which is shown is 7.9, the central line is 0 because this is the mean value, as already we know. Now, if I consider plus minus 3 sigma, the sigma value is already 1, hence the upper control limit would be plus 3 as shown here, and the lower control limit will be minus 3 as shown here. So, any calculations further to try to highlight why those values are central line, upper control, lower control would basically be rudimentary, because we already know we had converted that distribution using the standard normal concept to a standard normal deviate and drawn the charts accordingly. Thank you, and I will end this 29th lecture and continue with the 30th and the further on for the TQM1. Have a nice day.